All right, folks, let's do number 28. Could a particle moving with a constant speed of 3 meters per second on a path with a radius of curvature 2 meters have an acceleration of magnitude of 6 meters per second squared? Yes or no? I encourage you guys to pause this video and to give this problem a shot. So keep in mind, folks, we are talking about an object moving in a circular motion. I did play around with the mathematics a bit. And yes, you could technically make this work, and they have. Now, one thing to consider is that I'm going to talk about realistic scenarios, folks. And let me see what, I guess I'll use blue for the acceleration. So let's say you have the centripetal acceleration. Let's say you have some radius. And let's call that r. And let's say you have a tangential speed. And you call that v. Well, let me, all right. All right, folks, let's try this again. So let's say you have a, oh my God, I didn't realize how off-center that looked like. So let's say you have a circle with some radius. And let's call that radius r. And let's say you have some tangential speed. Let's call that, actually, let's put this on top. It doesn't really matter which direction this radius is. So let's just pretend it's momentarily, it's going to be on top. You can always flip the circle anyway, so it doesn't really matter. So let's say that this circle is going to be right here. And this is going to be the tangential speed v naught. And the acceleration, let's define that to be right here. Let's say there's a component of the acceleration that's going to be called a radial. And we know by the formula, by definition, a radial is going to be v naught squared over r. Or in this case, I'm just going to call it v. We are given, so for part A, we are given the instantaneous speed, which is going to be the constant speed of 3 meters per second. Well, I say constant speed, but realistically, the speed could vary. And you have a radius of 2 meters. So that being said, folks, 3 meters per second, v squared over r, which is going to be 2 meters. And that's going to be the a radial. So a radial is going to be 4.5 meters per second squared. Now, the question for part A is asking, since, you know, the calculation is the easy part, could the particle moving with a constant... With I'm not even high on the cannabis either, but could a particle moving with that speed on the 3 meters per second on a pathway of radius 2 have an acceleration of magnitude of 6 meters per second square? Now, you would think that the answer is no, and generally it would be no if it had a constant speed. However, let's presume that the speed changes. Let's say that there's a component that allows the speed changes, because remember, acceleration also has to do with the direction. There could be another component associated to this acceleration. So what would cause the speed to change? Well, let's just say that there's going to be some magnitude here. This is going to be some a tangential, and I'm going to put my own notation here. And the components for the acceleration is going to be a radial and a tangential. This is just my notation, the way I like to use it. So, and this is not necessarily an x and y point. This could be any points, but I'm going to define this to be this first column as the radial component and at as the tangential component. So let's take the magnitude of a, and let's define that to be a radial square plus a tangential square. So let's say that the magnitude of a has to do with the components of a radial square plus a tangential square. But what is the magnitude? Notice that the magnitude here is going to be this component right here. And this component is going to vary depending on what AT is. So there's going to be a little angle associated with this. And we could define this angle to be, well, let's just say that A radio is the same. That doesn't change, of course. But let's say that AT does change. So let's say that this increases the acceleration. So could this acceleration be 6 meters per second square if the magnitude of A radio is going to be 4.5 meters per second square plus AT square? What would AT have to be in order for this to be at least 6 meters per second? Well, according to the math, a tangential could potentially be 15.75 at the bare minimum for the magnitude to be 6 meters per second square. So that is the answer. So the answer is indeed yes. Could an acceleration with the centrifugal radius have that magnitude? Yes. Yes, it could. Now, this makes sense, folks. Now, I do want to emphasize that in a realistic scenario, this would really, and I mean really, increase by the A radio acceleration if it keeps looping at that pathway, because in order for this math to work, math states specifically that A radio is V naught square over R. So the math implies that whenever you increase the velocity, or if you increase the acceleration, momentarily you're going to really make this go faster and faster, like by a factor of t squared. So it's going to go really fast. The A radio is going to really increase over momentarily of time. So you're going to have a really oscillating, I don't know, the time between those periods, that's going to get less and less and less. So it's going to go really fast. And I'm saying realistically. I don't know how people model these, but whatever. Anyways, could it have a magnitude of 4 meters per second in each case? If the answer is yes, explain how it could happen. So now let's answer part B. Could it have a magnitude of 4 meters per second square? Well, think about the magnitude. The magnitude of the acceleration is going to be, it already has A radio. A radio is 4.5 meters per second square. The Pythagorean states that A square plus A tangential square is going to be, you know, whatever, some component depending on what that A tangential is. Now, if A tangential is 0, well, the magnitude is going to be 4.5 meters per second square. So that means that whatever that value is, there's nothing you can increase. You can change the direction of the magnitude, or you can change the direction of A tangential, but the magnitude will always be, at the very least, A radial. So the answer is no for that one. There's no way, regardless of the A tangential, that you could have a magnitude of 4 meters per second square, unless presuming that you change the AT and put it in the direction that's opposite the velocity. But then again, and that would only be a circle for that momentarily when t equals 0. But at t equals 0.1 second, it's not going to be a circle anymore. It's going to be some elliptical pathway or whatever. So I know I spent a lot of time on this video, but the conceptual is very important, guys. So, and I didn't really read the book, to be honest. Well, I did read it a long time ago, but I didn't really cover this when I was doing this. I was just working out the math. But you know, you don't need these things to be explained to you guys. Like, the whole purpose of this video is so that you guys can be independent in your mathematics. Anyways.